Hello friends, today we are going to see how to design lifting lugs. What are the lifting lugs? Why these are required in any component or in any equipment? What is the purpose of that? How many types of lifting lugs are there? So what we are going to cover is type of lifting lug. Then lifting lug arrangement. There are various arrangements by which we can lift the equipment. Then standard uh, selection, standard lifting lug selection. Then horizontal to vertical lifting lug formula derivation, and then design procedure in PVD and in CodeCal. So let's begin with this lecture, wonderful lecture. So typical lifting arrangements for the vessel. We can see over here. Let's start from the topmost left side. We can see from here. So this is the equipment. This is typically a vertical equipment, as we can see over here. Flared type of skirt support is there, and there are some tailing beams also have been provided. Why those? Because to reduce the stresses which will be generated at the time of lifting this equipment when there will be a tailing lug at the bottom. So we will be holding with the trunnion at the top and the tailing lug at the bottom. So this shape of circular can become oval. To avoid that, there will be this tailing beams have been provided. So you can see from here, these are nothing but the tailing beams which are going to restrict the deformation that is supposed to happen at the time of making this equipment from horizontal to vertical. So that is one tailing beam, and just after that tailing beam there will be tailing lug. So that is one thing. Another thing, if you can see over here, there are number of transportation saddles have been shown. Why these saddles are there? These are just for the transportation purpose. When this equipment will make vertical, these saddles will not be in place. So this is just for the transportation purpose. This yellow color, if you can see, these are the beams. These are called as the lifting beams. These are lifting beams, and this is nothing but the lifting rope, or we can say lifting belt, so which have been used over here to lift this equipment from one place and to mount on the another. Please do remember, this is the a picture that has been taken from the this is taken from the shore, right? So where it is going to mount on that, mount on the vessels, or we can say the ship at the time of transportation. So this, if we can see, this is not to make this from horizontal to vertical. This is just to lift it from this place and to place it horizontally on the another. If it would have been used for the purpose of making it vertical, the way we are seeing over here, there is a tailing lug or tailing like this, and there will be lifting lugs or trunnions. So you can see over here in this particular equipment, it is the arrangement by which the equipment will be erected, that will be made vertical with reference to this. These are nothing but the trunnions. You can see over here. So there is trunnion on this side, another trunnion on the another side, and from that the lifting belt will be positioned. So earlier the equipment was vertical, then it had made vertical, horizontal, and then it has made vertical with the help of this trunnions. And at the bottom you can see over here there is one tailing lug. So that tailing lug will place, or that tailing lug will be holded, will be attached with one beam connection like this. There will be a lifting arrangement. There will be D shackle which will be placed in that tailing lug, and then it will be attached with the crane. So here there is one crane which is holding that tailing lug, and here there are two trunnions from which the belts will be there, and that will be that belts will be attached to one spreader beam if at all it has been used. If not, then it can be, you can see over here, this is a spreader beam. So you can use spreader beam like this, or else you can lift with the single point lifting. So this is with spreader beam. Similarly, here also they have used spreader beam at the top. So the rope, whatever we are going to see, that will just go in one plane. That will be in vertical direction. That won't have any angle. Here we can see there is no angle. The chain or the belt which is in vertical condition. But here if we can see, it is making one angle of lifting. So it depends upon the lifting philosophy, and accordingly the forces which are coming on those trunnions are also going to get changed. If it is to be lifted with the help of spreader beam, there are only vertical forces which will be coming, or tangential forces which will be coming. But if it is been lifted by single point, Then there are two components. One is the vertical component and another is the normal component. So that normal component will come into the picture. If there is an angle directly, single point lifting like this will be there. So let's come back to this. So this here we can see the belt have been shown over here. So these belts are just to put the vessel from one place to another. This is not for the purpose of making it horizontal to vertical. To make it horizontal to vertical, here there will be one tailing lug that must have been used, and there will be some trunnions at the top. Those must have been used. So this is these saddles are transportation saddles, and this is a equipment which is going to be transported, and this is how the erection will be done from horizontal to vertical. There will be one tailing lug and those two trunnions over there. So these trunnions will be get attached with the lifting belt, and that belt will be attached to the spreader bar like this. So there will be a spreader beam or spreader bar to which these belts will be attached, and then from bottom the tailing lug will be having one D shackle, and that will be getting attached with this crane, and this is how it will be made from horizontal to vertical. So the belt will go on twisting, or we can say rotating inside the trunnion, and it will make it vertical. So once it was horizontal, so there will be forces which will be coming, half the load which will be coming on the trunnion and the half the load which was coming on that tailing lug. The moment we will make it vertical, the vertical reaction or the load on the trunnion will be on the higher side, and the load on the tailing lug which will be reducing. And once the equipment will be 100% vertical, so there will be no load on the tailing lug. All the load will be transferred to this trunnion. So how this lifting positions will create a variety of the forces, and how to resolve those forces, that also we are going to see. So here the purpose is how these lifting arrangement, lifting trunnions, lifting lugs, you can see over here. This is also lifting lug, two on this side and two on another side. So here also we can use spreader beam, or we can use with the help of a single point lifting. So here you can see there is one lifting lug over here and another lifting lug. This is a stack type of heat exchanger. This is stack. Stack means it will be placed one over the above. There is one bottom heat exchanger. It will be having its own saddle, and it is also having another equipment which will be placed on top of the bottom heat exchanger. And this lifting lug will be used for lifting this entire stack heat exchanger. So this is also one of the type of lifting lug. Here also you can see one lifting lug on this side, one lifting lug on another side, and there is one tailing lug at the bottom. Here there are four lifting lugs. Here we can see there are trunnions. Here we can see there are trunnions and a tailing lug. So it depends upon when to go for which type of arrangement, when to go for lifting lug, when to go for trunnion. That is what we are going to see in the upcoming slides. So this is just to give you an overall idea that how the lifting will be done. Then different types of lifting arrangements. You can see from here the lifting lugs over here. The top three are the lifting lugs. You can see it can be have the shape like this, and it can have a shape like this. So what is the difference between this and this? You can see over here the radius and the base is having the same dimension, whereas here the base is bigger but the radius is on the smaller side. So what the difference in the design or the strength it is going to make? So in shear, the width which is available in this case will be from this to this, and here it is from this to this. So here we can see that the shear strength or the shear area, rather we can say, is more in case of this type of lifting lug rather than this type of lifting lug. The base will be the same, let's say. So because of the base, the bending moment resistance will be the same at the bottom, but at the top we can see the area available between the edge and the whole edge is called as ligament. That is lower over here, that is higher over here. So this is have the higher ligament, higher shear area, so it will give you higher shear strength. So here also we can see the base is bigger, and the central hole or the rather the hole is not central, it is off centered. Here it is centered in line with the base, it is also exactly at the center of that base, but here it is not exactly at the center, it is at the offset distance from the center. Why this will be required? That we'll going to see in upcoming slide. So this is also nothing but this, but it is having a more curved radius. It is not having any straight portion like this, and this is a typical type of trunnion. So trunnion consists of one pipe and one closure plate. So this here it is welded on some square box. Otherwise, it will be directly welded on your vessel. So this trunnion will be directly welded on the vessel. It will be having a pipe like this, and it will be having a closure plate. The purpose of this end plate, closure plate, uh, is to keep the lifting belt within this trunnion surface. Otherwise, it will slip down from this. So to keep it over there, this plate will be used. So why trunnions to be used? Why lifting lugs are to be used? That also we are going to see. So this is a typical lifting arrangement for horizontal vessel. You can see over here there is a saddle. This is a horizontal vessel with saddle, and there are lifting lugs. Okay, so the lifting lugs depends upon the amount of weight it is going to lift. We can provide either two lifting lugs like this. You can see over here. This is a lifting lug, right? So there are only two lifting lugs, one over here, and we can lift this with the help of single point lifting. Only one crane. So one belt will come from here, one another belt will come from here. There will be a hook and there will be a crane. So what will happen? This is called as a single point lifting. This is called as a single point lifting. We can either use a spreader beam also. You can see over here spreader beam. So if there is a beam has been used, then here from the straight component come, here from the straight component come, and it will be lifted like this. So you can use spreader beam. You can lift the equipment without spreader beam. What effect does that will have on your lifting arrangement or the stresses? That also we are going to see. So when there is a spreader beam, we can see that there is only vertical reaction which is coming into the picture. But if it is a single point lifting like this, then at the time of designing, we have to resolve this force in two components. One is the horizontal component and another is a vertical component. So because of this single point lifting, vertical component will definitely there. In addition to that, the horizontal component will also there. With the help of spreader beam, there will be only this vertical component. There won't be any horizontal component unless and until there is some angle over it. So one component will be reduced, and hence the stresses or the bending moments caused by that component will also be reduced. So the combined stresses will be reduced if we are using spreader beam. So here there are two types of arrangement. You can have the lifting lugs like this with spreader beam or without spreader beam. Here you can see the same arrangement over here, but this is without spreader beam. This is single point lifting. So here is one single point lifting over here and another single point lifting over here. So this is a typical arrangement for lifting of that equipment. So let's come over here. So WE is nothing but the weight of that particular component. WE is nothing but the weight of that component. So these are nothing but the lifting lugs, perpendicular lifting lugs typically will be used. This is the lifting angle with reference to the horizontal. It is usually shown in case of vertical. That is the half apex angle or the full apex angle is 30 to 45 degrees usually preferred. Lesser the angle, lesser will be the normal forces, or we can say the forces along the axis will be come into the picture. Theta is nothing but the sling angle. PL, this is representing PL. Actually, there will be a belt or rope like this. So PL is the load acting on the sling. That belt or the rope or chain is called as a sling. So PL is nothing but the load which is acting on that sling. And this is nothing but the weight of the equipment, which we assume to be concentrated at the center of gravity. So this point represents the CG of that vessel, and WE is the weight. So if the vessel is having the same geometry, equilateral geometry, or we can say symmetric geometry, so the saddles are placed at an equidistance from this CG, then what will happen? The entire load, W is, let's say, the total load. So half load will be coming as a vertical reaction over here, and half load will come as a vertical reaction over here. So in this lifting lug, we can say this P, if we are using single point of lifting, so this will be equal to WE, because under equilibrium of forces, your all vertical forces have to be balanced. So W is downward, so P is vertically upward, so P will be equal to WE, which is nothing but the CG. But this P is not, this will be distributed for this lifting lug and this lifting lug. And for this lifting lug, the vertical reaction will be how much? Let's say again in the equilibrium condition, the forces must be balanced. So the downward forces and these upward forces will be balanced. So whatever load is there, if these lifting lugs are equidistant from this CG, so half load will come over here and half load will come over here. So this load will be equal to how much? This vertical reaction will be equal to how much? WE by 2. WE by 2. That is weight by 2 will be the vertical reaction over there. And then we can calculate the component which is acting over here, and that component will be calculated with the help of this vertical component, that is nothing but WE by 2, which is nothing but 0.5 times of W divided by sine theta will give us, by using the trigonometry, the vertical is known to us, that is WE by 2, that is nothing but 0.5 times of W or WE. And this reaction will be calculated as sine theta is equal to vertical reaction divided by this hypotenuse. So the hypotenuse is nothing but the PL, that is a sling force. So PL will be equal to 0.5 into W, that is WE by 2 divided by sin theta. So by this formula we can calculate the sling reaction. So this sling reaction, people usually what does, they'll take half as this WE by 2, they'll take as a sling reaction, which is absolutely wrong, because under equilibrium of forces the vertical reaction have to be balanced. So this vertical reaction will be WE by 2 and this sling reaction will be WE by 2, that is 0.5 times of WE divided by sine of this angle theta. So that this is how we have to calculate this PL. Now let's say a lifting of vertical equipment or making it from horizontal to vertical. So here we can see for the small vessels there will be one tailing beam or tailing lug. These are the tailing lugs, these are the lifting lugs. This is tailing lug, this is lifting lug. So one tailing lug will be given exactly at the center of these two lifting lugs. You can use either the spreader or single point lifting like this. If there is a spreader, there will be a vertical reaction will be coming into the picture. And if there is a single point lifting, then there will be one horizontal component and one vertical component will come into the picture. So now in shop mostly, even though we are providing the lifting lugs, there are some practices those will be followed by the contractors or the shop worker, that instead of engaging the lifting lugs in the lifting process, they are usually take the help of this nozzles. Actually these nozzles are not designed for lifting purpose, right? So if you have the belt over here, there are chances that this nozzle can bend, right? And if this nozzle will be bent, then what will happen? The counter piping which will be coming, that will not match exactly with this and there are chances of leakage. So never ever use this nozzles for the lifting purpose. Also there are chances that people are also using the legs for the lifting purpose. Again, the legs are not designed for lifting purpose, right? So if we are going to use that for the lifting purpose, there are chances that this may also slightly bend, and because of that this equipment will not be 100% exactly vertically mounted, and none of the nozzle flanges will match with the counter flanges. So there will be some problems while doing the assembly of this, and because of this there are chances of leakages between the flange joints between the nozzles and the mating flange. So that's the reason why never use these nozzles or the legs for the lifting purpose, as you have to design it properly, the lifting arrangement, either the trunnions, lifting lugs or some another arrangement what will be used. So that arrangement only have to be used at the time of lifting the equipment, and do not use any nozzles or the pipe legs. In case of large vessels, you can see over here, this is a very large size of lifting. So for the larger vessels, the trunnions are or the standard heavy lifting lugs are used. So usually it is said that for the heavier vessels, instead of lifting lug, we are going with the trunnion. So what's the reason why we are going with the trunnion and not with the lifting lug? Can't we design lifting lug? Lifting lug you can design for any size. Okay, lifting lug you can design for any size, for any weight. Then why we are going for trunnion then? Because the reason being, When we are looking at that lifting lug, you can see over here. So the lifting lug will be having one section modulus, which is called as a strong axis section modulus, or the moment of inertia in strong axis. So where this entire width of that lifting lug will resist the forces which will be coming. So let's say because of this, there will be one vertical force coming like this. So that vertical force will be resisted by this entire width of the lifting lug. But there will be one horizontal force will be coming, right? Because of this. So because of this horizontal force, it will be bent across its thickness, across its thickness. So thickness is not much. So its section modulus along the thickness is called as a weak section modulus, or we can say one is a strong axis, another is a weak axis. For this lifting lug, this axis is the stronger one, right? But the one which is going inside, if I'm trying to push this lifting lug from this side, it will easily bend across the thickness because it is having a weak axis, because only the thickness is going to resist. And that's the reason why we usually not prefer the lifting lug to be lifted across its thickness, or else we provide some gussets to have that control in that bending moment. So what's the reason? Because the lifting lug are having two axes. One is the strong axis and another is a weak axis. Strong axis is across its width, like here. So if it is going to there will be some forces acting like this. Because of that, there will be some bending moment. So the stress caused by the bending moment will be calculated as stress is equal to m upon z. That is, m is the bending moment divided by z is the section modulus. And in this case also there will be some force acting. Because of that, again the moment will become. But here the section modulus will be the strong axis section modulus, and here across thickness the section modulus will be the weaker section modulus. The formula is BD cube upon 12 to calculate the moment of inertia. So BD cube by 12, in this case the cube will be the width cube and the thickness will be the multiplier. But in this case, the thickness cube will be there and the width will be the multiplier. So we can see in case of lifting lug, its strong and weak axis are having huge difference. It is having a huge difference. It can be 7, 8 or 9 times the difference in the value of the moment of inertia. So the moment of inertia in strong axis is almost 8 to 10 times higher than that of the weak axis. So it may require very thin thickness if we are going to lift the equipment across its width. But if we are going to lift it across its thickness, like here, then the thickness will be on the very higher side. But if we deal this with the Trunnion, Trunnion will be having a pipe which will be having a circular cross section. It doesn't have any strong or weak axis, because it will be having a uniform moment of inertia in all the directions, and it will be calculated by pi by 64 d raised to 4. And if it is a hollow, then d raised to 4 minus di raised to 4. So by this formula we are going to calculate moment of inertia. So let's say for the same weight of the lifting lug, if I'm having some plate and that plate weighs around, let's say, 10 kg. So that 10 kg of that lifting lug weight, and if 10 kg of the Trunnion weight, that Trunnion equivalent to 10 kg weight can lift very high loads as compared to the plate, because it is having a uniform moment of inertia. So even you can use it with a spreader beam or without spreader beam, it will have the same moment of inertia. That is not true for the lifting lug, and it is having very higher value as compared to that of lifting lug. That's the reason why at the higher loads or for the heavier equipment, Trunnions are more preferred as compared to those of the lifting lug. What's the reason? Because the Trunnions are having more uniform moment of inertia in all the directions. So let's say we are going to lift the equipment or the column, and we are going to make it vertical from its horizontal position, because whenever it will be manufactured, it will be in a horizontal position, it will be transported horizontally, and then at the site you are going to lift it, you are going to make it vertical. So how that is to be done? So let's say this is the angle theta, which is the angle with reference to let's say this is the angle with reference to the base, or we can say the land, or we can say the datum. This is the angle theta. WL represents the weight of that equipment, and this point represents its center of gravity. So this is CG, and this is the weight of that equipment. There is one tailing lug over here, and there will be lifting lugs over here, right? So as we are going to have the lifting lug and tailing lug in equilibrium condition, these force will be balanced by two reactions. One is the tailing lug reaction in counter direction. This is downward, this is upward, and another is the force P. Correct? So for this CG, there will be vertically downward force, and at the tailing lug, there will be counterbalancing force. It is in vertical direction, and here the P force will be in vertical direction. Because of this P force, if we compare this P force as along and perpendicular to the axis of the lifting lug, so we will resolve these force along the lifting leg axis and perpendicular to the lifting leg axis. So one component is along the length, so that will be PL, and another is in the transverse direction, so that is PT. So because of this P force, there will be PL and PT. And similarly, because of this T force, there will be FL and FT. You can see over here, FL and FT, these are nothing but the component of this vertical reaction in along the length and perpendicular to the length direction. So we are going to calculate at various angles how these tailing leg reaction and the lifting leg reaction are going to get changed. How to calculate the value of this based upon this angle and based upon the equipment weight. So let's calculate, let's draw one free body diagram. So this is the actual case and this is the free body diagram. This is taken from Dennis Moore. The free body diagram of this lifting arrangement. So let's say WL represents, so this line represents the axis of that equipment. Here we can say this is a CG, WL is the force. You can see over here, theta is the angle with the horizontal. Then we can say WL, that is nothing but the weight of the equipment at the CG. Then T is nothing but the tailing lug reaction. T is nothing but what? The reaction at the tailing lug. P represents lifting lug reaction. Then L1. L1 is the length that is from lifting lug to tailing lug. The total entire length between lifting and tailing lug is represented as L1. This is nothing but this length from the lifting lug to the tailing lug. Then L2 is the distance from the center of gravity to the lifting lug. We can see from this point to this point, this distance will be represented as L2. The L2 over here from CG to the lifting lug, that is distance L2, and L3 is the distance from the CG to the tailing lug reaction. You can see over here L3 is the distance from the CG till the tailing lug reaction, and L4 you can see over here, L4 is the distance between the center of this tailing lug and center of the axis. So you can see here the axis is like this and the tailing lug is offsetted. It is not exactly at this point, right? So this distance between them is called as a distance L4, which is represented over here. So this is a free body diagram. Once again, we'll have a look at this. P is the vertical reaction. T is the vertical reaction at the tailing lug, or we can say tailing lug reaction. P is lifting lug reaction. It will be resolved along the axis and perpendicular to the axis of the vessel or lifting lug. So PL is P sin theta and PT is P cos theta. Theta is the angle. This. Then the reaction T will also be resolved along the length and perpendicular to the length. FL and FT are the forces. FL is equal to T cos theta and FL is equal to T sin theta. So this is nothing but the free body diagram. Now let's project all these values down over here to calculate the values of the various forces. So let's say this is the point of reaction of the tailing lug. This is point of reaction of the lifting lug. So here there will be P, here there will be T. This represents the weight of that equipment, and this is the overall projected length. So if we look from the top, it will look like this. So there will be a reaction like this, a T and P, and there will be a weight which will be acting in downward direction. And these are the resolution of these distances in horizontal direction. So here this L2 cos theta will give you this dimension. Here L3 cos theta will give you the dimension between this horizontal dimension, and here L4 sin theta will give us the distance this, and from this to this the entire length will be L1 cos theta. The L1 cos theta will be the distance from this to this. So L1 cos theta is this distance, L2 cos theta is from weight to the vertical reaction, and L3 cos theta is from this point of the axis till the WL, and L4 sin theta is the distance between these. So this is a free body diagram. So this is how it has been mentioned in. So let's enlarge this value and look at how it will look like. So this is the enlarged view of that resolution of forces or the projected forces. So we can see over here WL is a vertical reaction, which is weight of the equipment acting downward. T is the tailing lug reaction and P is the lifting lug reaction. Now let's calculate, resolve these forces in vertical direction. Under equilibrium of forces, we can say WL is equal to T plus P, isn't it? WL is equal to T plus P. So we can say P is equal to WL minus T. It is a simple mathematics by which we can calculate if we know the value of weight, which will always be known to us, and the value of the tailing lug reaction, then we can calculate the value of lifting lug reaction. So P is equal to WL minus T. So by this formula, we are going to calculate that. Now, taking the moment at point T. So under equilibrium condition, summation of moment is equal to 0. So we are going to get moment over here at this point. This is not given in Dennis Moss, but this I have derived so that you will better understand from where that formula has come from. They have directly given the formula. So let's say this is the weight of the equipment, this is tailing lug reaction, this is lifting lug reaction, this is the angle theta. So how to calculate the value of this force T at various angles with reference to W. But we are going to derive it first so that you will better understand. So the taking moment at point T and resolving the forces, we can see at point T. Let's calculate the moment. So there will be one moment, that is WL. What is moment? That is force into perpendicular distance. So WL multiplied by this total distance. How much is that? L3 cos theta plus L4 sin theta. So you can see over here WL multiplied by L3 cos theta plus L4 sin theta. This will be counterbalanced by the moment caused by this reaction P, or we can say this is downward, so this is minus, this is plus, and this will go on the other side, so you will get the same equation. So it is equal to the force P multiplied by this total distance. How that total distance, which is L1 cos theta plus L4 sin theta, isn't it? L1 cos theta is this distance plus L4 sin theta is this distance. So basically the distance from the lifting lug reaction till the tailing lug reaction is entire distance is the moment arm for this force, which will create the moment at this point, and WL into L3 cos theta plus L4 sin theta is the distance which will going to create a moment at this point. So under equilibrium of the forces, the moment caused by WL and the moment caused by P will be having the same value. So that's why they both have been equated. So WL into L3 cos theta plus L4 sin theta. Let's solve this. P is nothing but what? P is WL minus T. The value of P we can replace it with WL minus T. So instead of P, we will be using WL minus T. And let's solve this bracket. So WL into L3 cos theta plus L4, WL into L4 sin theta is equal to WL into L1 cos theta plus WL into L4 sin theta minus T into L1 cos theta minus T into L4 sin theta. So what will happen if we closely look at WL L4 sin theta and WL L4 sin theta? These two terms will get cancelled because it is plus. If it is come on this side, it will be minus. So plus minus get cancelled. So now how this equation will look like? WL L3 cos theta is equal to WL L1 cos theta minus T into L1 cos theta minus T into L4 sin theta. If we look at L1 cos theta, L1 cos theta, this is nothing but the distance from this to this place, and this is nothing but L2 cos theta plus L3 cos theta. So instead of this L1 cos theta, we are going to put L3 cos theta plus L2 cos theta. This L1 cos theta is the distance from this to this place, that is nothing but L2 cos theta plus L3 cos theta. So let's put that value over here. So WL multiplied by L1 cos theta, instead of that L2 cos theta plus L3 cos theta minus T into L1 cos theta minus T into L4 sin theta. So now we can see WL L3 cos theta and WL L3 cos theta. This term will get cancelled. Now the reaction will look like this. that is minus minus. If we come on this side, it becomes plus. So T into L1 cos theta plus T into L4 sin theta is equal to WL into L2 cos theta. So if T is to be calculated, T will get common and the bracket term will go on the division on the right side. So this is how the formula will look like. T is equal to WL L2 cos theta divided by L1 cos theta plus L4 sin theta. This is the formula which is directly given in Dennis Moss, and this is how we have derived that, how that formula have come from. So if the weight is known to us and the angle of lifting or with horizontal is known to us, then from this simple equation we can calculate at various angles what is the value of tailing lug reaction we will be getting. And once the tailing lug reaction is known to us, then with the help of this equation we can calculate the value of P also. So how to calculate P? P will be equal to WL minus. So this is how at various angles we are going to calculate the value of various forces. So let's have one example and try to understand the philosophy of lifting the vessel from horizontal to vertical. So here there are two lifting lugs and here there is one tailing lug, isn't it? So this is in horizontal condition. Weight will be vertically downward, WL. Here there will be reaction P. Here there will be reaction T, isn't it? L3 is the distance from CG to tailing lug, L2 is the distance from CG to lifting lug, and L1 is the entire distance, L4 is the distance from the axis of the tailing lug to the axis of the vessel. By using the following equation, loads are calculated. We have seen the formula that T is equal to WL L2 cos theta upon L1 cos theta plus L4 sin theta. This is the equation directly we have to use in order to calculate the value of the forces caused by the weight and the angle of lifting. So here we can see the angle of lifting is how much? Horizontal 0. Cos 0 is how much? 1. So this term cos 0 will be 1. Sin 0 will be 0. So this term will not be there. This term will come 1. 1. This term also becomes 1. It is simply WL into L2 and T into L1. So this L1 come on this side. So what has happened? How to calculate T? T is equal to WL into L2. WL into L2 cos theta is nothing but 1. So it is simply WL divided by L1, the entire distance. That will give you the tailing lug reaction. And how to get the lifting lug reaction? It is nothing but WL minus T. So now at various angles, now if we look at over here, the CG is L3 distance, you can see mark over here, L3 is more than L2. So the CG is shifted towards the lifting lug. The CG is shifted towards the lifting lug. If the CG is towards lifting lug, then the load on the lifting lug will be more at the time of lifting and on the tailing lug will be lesser. So if at the angle 0 is there, means it is exactly at the horizontal position. We can observe the reaction forces at T and P. If CG would have been exactly at the center and L3 is equal to L2, then T and P forces would have been the same value. But here we can see as the CG is shifted towards the lifting lug, so the P value will have to be more than the T value. So it is evident from here also. The entire load is 400 kg, let's say 400 pounds, kilo pounds, that is what, or else we can say it is 4 ton, let's say. So it is 171.7 and 228.3. So if we add these both two, it becomes 400. As the CG is shifted towards P, so we can see over here the value of P is more than value of P. So if we put value of theta is equal to 0 over here and the weight of that equipment as 400, so you can easily calculate the value of T and P. So from here also cos 0 will be 1. So this term will not be there. Only WL, that is 400, divide by L1 cos theta plus L4 sin theta. Sin 0 will be 0. So this term will not be there. Cos 0 will be 1. So only L1 will be there. So L1 is the entire length. So if we divide by that, we will get the value of WL upon L1. And that value is nothing but 171.7. And P is equal to WL minus T. So 400 minus 171.7, it becomes 228.3. That is nothing but the value of P. This is how we are going to calculate. Now, once this vessel is going to be lifted like this, you can see the angle will keep on changing. It increases from 0 to 10, 20, 30, 40, 45, 50, 60, 70, and at vertical condition you can say that it is 100% vertical, and all load will be coming on the lifting lug. There will be no load on the tailing lug. So you can evident from over here. It is evident from here also. If we look at the angle as it is going on increasing, the tailing lug reaction is going to get a decrease, and it will be equal to 0 when it is exactly at the vertical, when theta is equal to 90 degrees. On the contrary, we can see the value of the force P, or the lifting lug reaction, which is going to get increased as it moves from 0 to 90 degree, and at 90 degree entire load will be coming on the lifting lug. So you can see over here it is going to get increased, and at the vertical position when theta is equal to 90 degree, all load will be coming on this lifting lug, and hence all the load which is 400 kg will be coming on the lifting lug, and 0 will be the load on the tailing lug. So we can say as the angle is going to be increased, as the angle is going to get increased, the tailing lug reaction is going to get decreased, and the lifting lug reaction is going to get increased. It is evident from here. So this is how at various angles we are going to calculate the various forces, and usually what will be done, the maximum value in this and maximum value in this will be far more conservative. So these value will be considered in the calculation. At various angles we should calculate, but if we don't want to calculate at every angle the stresses, what we can do, we will take the worst from this and worst from this will never appear, but for the sake of calculation we are taking the most conservative values in both the conditions, and if it is safe in that conservative condition, then we can say it will be safe in all other conditions. So usually in this the worst value will be taken, in this the worst value will be taken, and for that worst, which will be a hypothetical situation for which we will design it, and if it is safe, then we can say there will be no condition at which it will fail. Otherwise, for each and every condition you need to calculate the stresses separate. Now let's understand the thickness calculation. How to calculate the thickness of any lifting lug. How to calculate the thickness of any lifting lug. So when we are calculating the thickness, we must understand the stress philosophy for this lifting lug, that what kind of stresses will be developed in this lifting lug. There will be shear stresses, there will be bearing stresses, and there will be tensile stresses, and there will be moments which will be a bending moment that will also come into the picture. So let's understand first the thickness due to the bending. Thickness due to the bending. So whether the force PL will cause any bending? No. The force P is going to pull it. So it will create tension in that component, but not the bending, right? Bend means it has to be forced into perpendicular distance. But whereas the force PT is going to bend this lifting leg. So because of PT there will be bending, because of PL there will be no bending over here, right? So how to calculate the bending moment? Bending moment is nothing but bending force multiplied by the total distance. So here the bending force is acting, and it will create a moment at the base. So from base the height is B. So PT multiplied by B will give us the bending moment, and the bending stress will be equal to M upon Z. M upon Z. M is nothing but the bending moment, which is PT into B, and Z is nothing but section modulus. How to calculate that? Let's have a look at. So this is a formula given in Dennis-Moss, that if you have to calculate the thickness based upon bending stress, it will be like this. The formula is 6 PTB upon A square into FB. Now what is this PT? PT is nothing but the transverse force. What is B? B is nothing but this vertical distance, that is nothing but PT into B is nothing but the moment. So this can be, we say, M, and divide by Z, which is a section modulus. So the section modulus for this component. So here we can see the force is acting in this direction. So this entire width A is going to resist that force, and that's the reason why A cube will be there for moment of inertia. And section modulus Z is nothing but I upon Y. I is moment of inertia, and Y is extreme fiber elongation, or the distance of extreme fiber from the neutral axis. So let's derive this formula also. Now we know that the bending stress is equal to moment upon section modulus. Stress is equal to M upon Z. What is this value of M? M is nothing but the bending moment, which will be created by the force PT. PT into B will give us the bending moment, isn't it? M is equal to PT into B, and Z is I upon Y. I upon Y. I is moment of inertia and Y is the extreme fiber distance from the neutral axis. Now, for a rectangular cross section, if I take a cross section, it will be a rectangular one. For rectangular cross section, how to calculate its moment of inertia? It is BD cube upon 12. I is nothing but BD cube upon 12. And here D cube means the part which is going to resist that force is going to get cubed. What is the component which is going to resist it? It is the distance A. So that's the reason why A cube will be there. And thickness will be a multiplier divided by 12. This is the moment of inertia of this rectangular cross section. If I take a cross section, it will look like a rectangle and it will be having a moment of inertia of TL A cube upon 12, which is BD cube by 12, where the cube will be happened for the side which is going to resist. So here is the thickness is going to resist this force? No, this width is going to resist it, and that's the reason why it is A cube upon 12. And what is Y? Y is nothing but A by 2. Y is nothing but extreme fiber distance from neutral axis. This is the extreme fiber, and from neutral axis means from the center, what will be the distance? A by 2. So Y will be equal to A by 2. So after solving this equation, A will get cancelled. It becomes A square, and this 2 will divide by 12 and it becomes 6. Correct? So this equation, the section modulus will look like TL A square upon 6. So the value of Z becomes what? TL A square upon 6. So this we are going to put over here, TL A square upon 6, and PT into B will be nothing but our bending moment. So this 6 will go on the upper side, and the formula will look like 6 PTB upon A square into TL. A square into TL. Now what we have to calculate? We want to calculate the thickness, and we are using the allowable stress as the value over here. So here TL go on this side, FB will come on this side. So if we rearrange the terms, so TL will be equal to 6 PTB upon FB, which will be coming on the downward side. So FB into A square. So this is how the equation will look like. So this is how we are going to calculate the thickness because of the bending moment or because of the bending. So as we can see that P is the reaction, it will create one horizontal and one vertical reaction. Because of the horizontal reaction, there will be a bending moment, and because of this bending moment, by this formula, we can calculate the value of the thickness that is going to be provided for that lifting lug to resist this much force, which is going to create a bending. What is the value of allowable bending moment? It is usually 2/3 of yield. The bending moment usually it will be 66% of yield, or we can say 2/3 of yield. So TL will be equal to 6 PTB upon FB into A square, whereas FB is allowable stress in bending, and it is equal to 2/3 of yield. Usually, as far as our engineering formulas are concerned, the fundamentals are concerned, the allowable stress in bending will be 2/3 of yield. That was the thickness based upon which stress? Bending stress. Now we are going to calculate, because of the PL there will be tension, right? So thickness due to shear and tension also we are going to calculate. Let's start with the shear. So shear means what? The area will get shear off. So shear can happen because of PL also and because of PT also. Actually what will happen? We will be having one D shackle over here. So that will be having a pin. So that pin, if it is going to be felt in shear, that will shear, because the shear can be because of PT or PL. Let's understand because of PT just for the sake of understanding. So let's consider the force PT which is causing the shear failure. The shear stress is equal to shear force upon shear area. What is the shear force? PT, which is the force which is causing the shear, and what will be the area? That will be the area which is going to get sheared. So as we can see over here, there will be a pin which is going to shear off this area. So there will be area which is going to get shear over here as well as here. So there will be two areas which will be going to get sheared. So one in line with this, one in line with this. So what is the area, cross section area over there? This will be equal to this shear area. Let's understand this. D1 is the diameter of the hole. So shear force will be PT, and what will be the area? That is nothing but this is the area in which we are interested. So this is the width, and the thickness will be its another dimension. One dimension is this distance from the OD of this or this ligament, we can say the length of that ligament, and the width is nothing but the thickness. So how to calculate the this distance from this to this? That is nothing but the total entire distance A minus whole diameter. This minus whole will give us this distance as well as this distance. So we want only this distance. That's the reason why it will be divided by 2. So A minus D1, so you can see over here, A minus D1, that is nothing but this distance and this distance divided by 2, which will give you the width in this direction, and the thickness, which will be going to get multiplied to this. This will give you the shear area. And there are two areas. One is at the top, one is at the bottom of that shear pin. So that's the reason you always know that shear will have the two areas. So that's the reason why 2 will be the multiplier. So 2 will get cancelled, and the formula will be look like TL is equal to PT upon A minus D1 into Fs, whereas Fs is nothing but allowable shear stress. Fs is nothing but allowable shear stress. Usually, allowable shear stress is considered as 40% of yield, 0.4% of yield. So SY, the value of yield is usually 200 MPa, and that multiplied by zero point 0.4 will give us the allowable shear stress. So that value if we put over here, PT is known to us, and A minus D1 if we put, we'll get the thickness which will be required for that particular lifting lugs to resist the shear force. So the shear force that can be caused by PT or by PL. In both the cases, it will be either PL or PT divided by A minus D1 into Fs. Because here, let's say the area will be from this to this. So here the area or the ligament will be different. The thickness will remain the same. But this will be how to calculate that? Then this radius minus this radius divide this radius minus this radius. So this diameter by 2 and this radius, if we do the subtraction, then that area can also be calculated for the value of PL force, which is going to calculate or which is going to generate the shear. So the thickness also we are going to calculate for the shear. One we have calculated for bending. Now we have checked for shear. Another force which will be coming over there is the tensile force. Because of the force PL, this lifting lug will be getting pulled from its base, right? It is going to pull it off. So that will create a tension at the bottom. That is going to create a tension at the bottom. So TL is equal to PL upon A minus D1 into FT. Again, we are going to prove it, how that formula has come from. So we'll better understand this. PL is nothing but the force because of which it is getting the lifting lug is getting in tension. So PL is the tensile force, we can say. So the tensile stress is equal to tensile force upon the area which is going to resist, the area in tension. So what is the area in tension? So let's say PL is the force which is creating the tension. What is the area at the bottom? A into thickness. A into thickness. So the tension will be there at the bottom, and at every cross section the same tension will be there. But here the area is weaker. Here it will be not having A into TL. Here it will be having A minus D1 into TL. So here it will be there are more chances of failure than at the bottom, and that's the reason why here the area will be at this cross section. We can see the area at this cross section, which will be look like this. So this is the area A, this is the width A, TL is the thickness, D1 is the diameter. So this purple color area or dark blue color area is the area which is going to resist that tension. So how to calculate that? A minus D1. So this is this width and this width multiplied by this thickness. So A minus D1 into TL will give us this purple color area which is going to resist the moment caused by the force PL. So PL divide by A minus D1 into TL will give us the tensile stress. But here what is our so we have seen that the equation will look like this. That is the tensile force divided by the area in tension, and the area in tension will be A minus D1 into TL. So that will lead to the thickness calculation. If it is under tension, then the thickness to sustain for the tensile load will be calculated by the following formula, and that formula is equal to PL upon A minus GL into FT. Usually the tensile stress will be considered as 66% of yield only. So the allowable tensile stress what we'll be using is 2/3 of yield only. It will be similar to that of bending. So this is how we are going to calculate the various stresses which will be applied in case of the lifting lug, which will be applied in case of lifting lug. So now let's understand for what are the various sign conventions. If we are going to see axial force, normal force, tangential force, in case of vertical equipment, how does that look like? In case of horizontal equipment, what are the forces which will be coming? So let's say if the equipment is vertical like this is its axis. In that case, if we look at the forces which are coming on the trunnion, then the vertical along the axis of the vessel, the force which will be coming, that is nothing but the axial force. So along the axis of the vessel, the force which is coming, that will be called as axial force. So here, if I'm using a spreader beam, then what will happen? There are only one vertical force will be coming like this, and that will be the axial force, isn't it? So this is nothing but the axial force. Then the one which is coming normal, if I'm using a single point lifting like this, so what will happen? One will be the vertical reaction and another will be the normal reaction. That the normal force will be coming if at all there is a single point lifting or there is some angle with reference to the spreader beam. If it is only the spreader beam has been used, then the reaction will be vertical only. There will be no component of the force which will be coming in normal direction. So normal direction only comes if there is a single point lifting or there is some small angle change with reference to the spreader beam. So this is nothing but the normal force, correct? And the tangential means which is tangent to the circle. So this is my cylinder and the force which is tangent to the circle, which will be the one which is going inside from this. So here I can see only a point over here to see that tangential force. So here you can see one point and that point represents the tangential force. Here also you can see that blue point, right? That represents the tangential force. So this is the axial along the axis. Normal to the axis will be the normal force and tangential to the circle or that cylinder will be the tangential force. So this is for vertical equipment. But if we are having the horizontal equipment, let's say, and we are going to lift it either by single point lifting or with the help of the spreader beam, then how these forces will look like? Now, please do remember. Now the axial force will be what? The axis along the axis of the vessel. It is nothing but a point, right? So the axial force is nothing but point. Here we can see the tangent to this circle will be the tangential force. So this one is nothing but the tangential force, correct? Here, the one which is tangent, so this is nothing but the tangential force. Another is normal, which will remain the same, normal to the axis. And here the axial force will be the one which will be represented by a point because it is along the axis. The axis cannot be seen from here. It will look like only a dot. So here the axial force you can see as a dot only. So it depends upon what kind of arrangement or in what condition we are going to lift the vessel. Accordingly, the forces which will be coming on the trunnion as well as on the lifting lugs will change. So we have seen in case of vertical, there was tangential force which will be showing a point. So whether the tangential force will be there, that will only be there if we are going to lift the equipment from some another plane, which we most likely not going to do. So whether all these three will come into the picture, yes, they can, but for that reason, we must be having the single point lifting and the lifting point will also not be in this plane. So that is also in some another plane where this lifting lugs are not there. So it is not in the plane of the lifting lug, that is in some another plane, then only these three forces will come into the picture. Otherwise, only the two forces will come into the picture. So let's understand what are the other type of lifting lugs, how they will be placed. So here we can see one equipment. Here there are four lifting lugs, two on this side and two on the other side of that equipment. So now these are not perpendicular lifting lugs, these are the radial lifting lugs. You can see from here. So if I extend the axis, it will touches to the center of my equipment. So these are nothing but the radial lifting lugs. So if these type of lifting lugs are there and I want to analyze those and I want to calculate the thickness of those lifting lugs, then how to resolve the forces, that is very, very important. So let's say W is nothing but the weight of that equipment. and there are four lifting lugs, two on this side and two on another side, and let's assume that all are at equidistance from the CG. So what will happen, this vertical reaction will be divided in the four vertical reaction, each will be coming at each lifting lug. So you can see over here, this is downward and this is upward. So the upward reaction will be having a value of W by 4 because there are total four lifting lugs, isn't it? So whether this will be the tensile force for that lifting lug, no. If we just observe that, though it is vertical, but that is not vertical with reference to the axis of this lifting lug. Is it? No. It is in the third quadrant, we would say. This is first or this will be in the second quadrant. So if I put this lifting lug like this, so this W by 4 will be coming in this quadrant. So is it perpendicular? No. So because of this W4, we have to resolve the forces in line with the axis of this lifting lug and perpendicular to the axis of the lifting lug. So one will be W by 4 into cos theta, that will be along the horizontal direction, and one will be the vertical direction, that will be W by 4 into sin theta, W by 4 into sin theta. So please do remember, though W by 4 is a vertical reaction, but that is not the vertical reaction along the axis of the lifting lug. So again, that W by 4 we have to resolve to calculate the forces which will be coming in the vertical and horizontal direction. So this is very, very important to resolve the forces. Now let's take one example. So let's say we'll be having one equipment. That equipment is having one shell, two distant, and it is equidistance, or we can say symmetric geometry. So its CG will be exactly at the center, and the weight of that component or that total equipment is 2000 kg. How much? 2000 kg. Now there is one lifting lug over here and another lifting lug over here. So what will be the forces and how to resolve those forces? As we know that under equilibrium of forces, the vertical reactions will be balanced. So one force will be in downward direction. So one will be in upward direction on this side, another will be upward direction on this side, and that will be half of this because it is equidistant from this. So the vertical reaction will be how much? W by 2, that is half of this. And here also it will be W by 2, which is 2000 by 2, so it will be 1000 kg. So 1000 kg is the vertical reaction, and from that we have to calculate the horizontal reaction F. So how to calculate F? F will be is equal to W by 2 divided by sine 30. This is the 30, and let's say this is nothing but coming over here. So sine 30 is what? W by 2 divided by F. W by 2 divided by F. And if I want to calculate the F, then F will be is equal to W by 2 divided by sine 30. So W by 2 divided by sine 30, this is how I'm going to calculate the value of the force F. And once the F is known to me, F cos theta will give me the horizontal reaction. So W by 2 divided by sine 30 into cos 30 will be the reaction which will be in horizontal direction. So F cos 30 is nothing but 1732. 1732. So W by 2 divided by sine theta is nothing but 2000 kg. So the value of F will be how much? 2000 kg, and F cos theta will be 1732. 1732. So F will be is equal to how much? 2000, and 2000 cos theta is 1732. So please do remember. So though 1000 kg was the vertical load, but because of the angle theta, the if the angle theta is 30 degree, this is 30, means this angle is how much? 60 degree. This is 90, this is 60, 60, 60, 120. So if this lifting angle is 120 in between this and this angle theta is equal to 30 degree, then this reaction force, because if this is how much? 120 and this is 30, means it is inclined more towards the horizontal. So naturally the horizontal reaction will be more. At 45 degree, both these reactions will be equal. And if the angle theta is more than 45 and if it is close to 90 degree, then the vertical reaction will be more and the horizontal reaction will be less. As it is 30 degree less than 45, so we can see that from here the value of horizontal force is more than the value of vertical force. Vertical is W by 2, which is 1000, and horizontal is F cos theta. F is 2000. 2000 into cos theta 30 will be 1732 kg. So 1732 will be the horizontal reaction. So these will be the reactions which will be utilized in calculation in the future. So let's understand the designing of lifting lug in PV lead. In PV directly you can design this type of lifting lug where you don't have to resolve any forces. You just have to place this lifting lugs and have to give the dimensions, and the software will do the rest of the work, and it will resolve all these forces and will calculate the stresses. So it will be a very straightforward procedure. But what if the lifting lugs are in another direction, and there we have to calculate the resolution of forces, and then the software will not give you directly the resolution of forces. There we have to calculate it, and we have to put these values in the software, and then the software will perform the calculations in code calc. In pvlit it will not happen if the lifting lugs in opposite direction. These are along the length, right? If it is along the circumferential direction, in radial direction, these type of lifting lugs cannot be done. So how to do that? So for that reason, let's understand what are the various screens or the data that we have to put in. So if we, this is the data taken from CodeCal. So in CodeCal, we have to go to legs and lugs, and therefrom we have to put this data in. So please remember, design pressure is 3.5, design temperature. Usually this temperature will be the temperature at which we are going to lift that equipment. So it will be the atmospheric temperature, because at that temperature it will consider the allowable stress value for that material. So even though your design temperature could be anything, but for the lifting purpose you have to mention it as a ambient temperature. Then OD of your vessel, shell thickness, corrosion allowance, tan to tan length, and shell material. If you put all this data in code cal, this will just be represented in the report. This will not be utilized anywhere, because here we are going to calculate the forces and we are going to resolve the forces, and those value we are going to give over here. In code calc, we have to give the weight of that equipment. Again, this is just the value which will be reflected in your report. This value will not be utilized in any of the calculation, because in code calc you are the person who are going to resolve these forces based upon this weight, and you are going to give the axial force, normal force, and tangential force directly to the software, and the software will perform the calculation thereafter. But if this would have been in PVLit, and the lifting lugs which can be done in PVLit, in that case you don't have to mention any of these values. The software will take care of that directly. So let's say this is the diagram. This is taken from PVLit. This is not shown in CodeCalc, but this will be the same diagram which is going to help us to understand what are the various inputs that we supposed to provide in the software, so that the software will perform the calculation. So first is the lifting lug material that properly we have to choose from the library. Then the lifting lug orientation to the vessel. We are designing perpendicular type of lifting lug. Another are ear type of lifting lug. Those will be placed like this on the equipment. So these are not the ear type. So these are the perpendicular type of lifting lug. Now contact width or the height perpendicular to the perpendicular of the lifting lug. So contact width or the height perpendicular lug of the lifting lug W. This is very, very important. People are often get confused with this. Even though it is written as height or width, you don't have to get confused. This is always the base of the lifting lug which will be get welded with the parent vessel. So here what will be its base? That will be W. So this is the dimension that you have to mention over here. Let's say it is 150 in this case. So this is the dimension that what is represented over here. Then thickness of the lifting lug. The thickness of lifting lug, as this also works upon that, first we have to give the dimension, and then the software will tell us the stresses. If the stresses are within allowable, then the design is safe. It will not give you the thickness. The thickness first we have to give, and then the software will give back to us the stresses after calculation. So let's say we have assumed that for the 2000 kg of that equipment, for and here we are designing individual lifting lug. Please do remember, here we are designing individual lifting lug and not all lugs together. So we have to calculate the value of the forces and the moments which are value of the forces which will be coming on that particular lifting lug, and for that we have to design that. So let's say thickness, this is the thickness which we have to enter over here. Then the most important dimension, another is DH. DH is nothing but the hole of that lifting lug. How much size of this hole we should be giving? This must be in line with the D shackle pin that we are going to use over there. So please do investigate in your shop that what kind of D shackles are there, what is their pin diameter, and accordingly the hole diameter just above that. Let's say the pin diameter is 40 or let's say 45, then we can say the lifting lug diameter or this diameter will be 50. So please do remember in bearing calculation, bearing area calculation, or in shear stress area calculation, we have to use the pin diameter only, because only that much area will come in contact with the pin. So this diameter we have to provide as the pin diameter. So dh will be equal to pin diameter, then this will be the radius. This radius should be chosen such that the D shackle can be properly maneuver all around this lifting lug. So there will be a dimension given in the D shackle. So this dimension should be within that. Usually it will be taken as equal to or just more than that of the diameter of this pin. So let's say the diameter of the pin is here, you can see 50. So it is radius as taken as 60 or 50. That is fine. If it is passing in the bearing or in shear stress, then this radius can be as low as 50 also. So this is nothing but this radius. These all dimensions first we have to assume, and then the software will perform the calculation. H is nothing but the height of this hole center with reference to the bottom of this lifting lug. So if we will be having exactly at the center this hole, in this case we are having this exactly at the same center, so our W value is 150 and its half will be exactly the height H. So here you can see it is 75 has been mentioned. So H is nothing but the height at which this whole center is located with reference to the base. Then off center distance, that is from the base at what height this hole will be mounted. So this off center distance will be a function, or this will be a variable which depends upon some factors that the D shackle can be properly fixed. This value we have to keep as minimum as possible. Because of this value there will be higher bending moment coming. If this value is higher, the bending moment will be higher and the higher will be the thickness. So this value we'll try to maintain as minimum as we can, but this value will also be governed by sometimes if there is some insulation. So that insulation also needs to be clear, and thereafter the D shackle can be placed over here. So if there is a insulation, that insulation thickness should be within this off center dimension. If there is no lift insulation, then this dimension can be as small as 75, 65 also. And if there is an insulation, depends upon insulation thickness, it can be 100, 200 or 150, 125. It depends upon the insulation thickness as well. So this is nothing but the off center distance. What is the logic behind? It should be as small as we we can keep as small as we. But here what we need to understand is this dimension should be sufficient so that the D shackle can be properly fixed. So when we are saying D shackle, I am going to show you how this D shackle will look like. So let's say how these D shackles will look like. This is how the D shackle. This is called as a D shackle, which will be having a D-like shape. Then there will be a bolt like this, and this is called as a pin. So that pin will be placed from another side. Then a nut will be placed, and you can see a pin over here. So that will not going to open that D shackle. So this D shackle will be placed inside the lifting lug. So let me just show you how it will be placed in the lifting lug. You can see over here there is a lifting lug, and this is bow shackle actually. Yeah, it is having a shape like a bow of a tie, so that's why it is called as a bow shackle. Bow shackle will have more dimension over here for maneuvering, and here a D shackle will be having a D-like shape. So here you can see the lifting leg will be placed like this. Then the pin will be inserted, or we can say that bolt will be inserted, and then here the locking pin will be arranged, and then this D shackle or bow shackle can maneuver all around that lifting leg like this. You can see over here the D shackle has been placed over here, and it can slide according to the angle of lifting. So if the crane pulls it in this direction, then this shackle come in this direction. That's the reason why the radius should be such that the distance between the whole of that center and the ligament or the radius should be such that this D shackle should not foul with this. So usually this height we have to keep in mind at the time of giving the dimension, which we have seen over here as the radius r. So the radius r should be sufficient so that the D shackle can be easily maneuver all around it. So this is typically a D shackle what we have seen over here. This is a D shackle, and this is how it will be placed on the lifting lug. This is very important that people are getting confused. And this is the pin diameter what we have to give over here. This is the pin diameter, that is what we have to mention over here. DH is nothing but that pin diameter. So we were at this point of off center distance. Then minimum thickness of the fillet weld all around that lifting leg. Usually it will be considered as thinner of the two parts welded. If you will be having a RF pad, then RF pad thickness will be considered as a welded dimension. That will be the fillet weld size. Then there is a very important dimension. Here most of the people are getting confused. The length of the weld alongside of the lifting lug. The length of the weld alongside of the lifting lug. Usually some people are taking two times of the distance over here. WL is the distance, if we just closely observe, that is not the distance from the, if you can see the hatch portion, that only represents the lifting lug, and the outside rectangle represents the welding area. So here if we observe WL properly, it is from this point till this point. So it is equal to W. That WL will be equal to W. And if we observe WB, which is the length of the weld along its width or along the thickness, it will be from outside of the weld to the outside of the weld. Usually people are taking WL as the length is on this side also and this side also. Please never do that. It will wrongly perform the calculation. It will consider it twice, and unnecessarily you will be in trouble at the later stage, because you are considering two times the length. Because the length, the way it is been mentioned over here, it is WL, that is the distance from this to this only. So here how much it is? 150. So that's the reason why we have considered 150. These are very important dimensions that you should remember where to mention. I'll be providing the guidelines for that in the form of PDF, so you will better understand. That will be with you. And length of the weld along the side of the weld or along the thickness, WB. Now please do remember, here the thickness of the lifting lug is how much? 16 mm, 1 6, and 6 mm is the fillet size what we have chosen, right? So 16 plus 6 plus 6, so 16 plus 12, it becomes 28. So that's the reason why WB has been considered as 28. And we don't have to add any fillet in the WL. WL is without any fillet. WL is actual length of this W. So that's why it is 150 and it is 28. Why I'm saying I'm correct? Once we are going to see the results, we'll try and understand how these dimensions have played a role in that calculation. Now let's say our equipment is horizontal, and these are the forces what we have to mention over here. We, if you remember, the axial force what we have calculated, it was having the value of how much? Axial force is nothing but along the axis, which is F cos theta, which was having a value of 1732. The same value we have put in, and another was the normal force, which is having a value of 1000. So you can see over here 1732, and normal force was 1000, and there was no force along the tangential direction. Means what? We are going to lift it in this direction. So there will be no force which will be going to pull it across the thickness, right? So the lifting will happen in only this plane. There will be no force in another plane. That's the reason why tangential force we have considered over here as 0. The impact factor. This is the factor by which the loads will be getting increased by. So if it is 1.5, so whatever loads we have considered, those will be getting multiplied by 1.5, and these higher loads will be utilized in the calculation. So whenever we are going to lift the equipment, there are chances that there are some jerks which will be felt, and because of that there will be some heavier loads which will be coming. So that will be taken care by this impact factor. This is minimum taken as 1.5. These guidelines you can see in Dennis Moss, that minimum value is 1.5. Sometimes a customer can ask you to design it for 2, the impact factor as 2. So there these values will be increased by 2 times, and for those the stresses will be calculated. Here in this previous image we have seen occasional load factor. People are often get confused with this. This is not the load factor by which your loads are going to get increased. This is the factor by which your allowable stresses are going to get increased. So never use this. value more than 1, because if let's say I'm using it 2, then the allowable stress the software is going to increase by 2 times. This is the occasional load factor as per AIST. We are never going to use this, so place this value always as 1. So this is the factor by which your allowable stress are going to get multiplied with, right? This is not the factor by which people often think that if I'm taking 1.5, so it is going to increase the load. No, it is going to increase your allowable stress. So never do that. So we have seen that all the parameters. Now, once we have performed the calculations, we will see the results will be appearing, and the results will appear like this. So let's analyze each and every part of that result. So let's concentrate upon the results for the lifting lug description. You can see that similar data will be appeared. So first is weld group inertia about the circumferential axis. Weld group inertia about the circumferential axis, and they have directly given you the values. Based upon the inputs what we have put in, the software have worked out these values. Now, whether you have put in correct values and it has understood correctly and it has taken the correct value or not, how to cross check it that. So we are going to calculate these values manually, and then we are going to cross check with these values, and then we'll understand whatever our assumptions or whatever the variables we have chosen, these values are according to that. So weld group, so there is a group of weld which forms a rectangle. It will be welded all across the thickness and the length of that lifting lug, and hence it forms a rectangle. So it is nothing but a rectangular area. It will be having a width of how much? 6 mm as the fillet width. So 6 mm fillet width will be the area. So that entire area along the circumferential direction will be having a moment of inertia of 542 centimeter raised to 4. Weld group centroidal distance in its longitudinal direction. So along the length, what its distance along the longitudinal axis. The weld group centroid distance along the length. So that will be 81. How that 81 has come from? It has not been given in the software. So let's prove that from where this value has come from, so we'll better understand. Then distance of the weld group centroid from the lug bottom. From the bottom of the lug, what is the distance and how that 75 have come from? Weld group inertia about its longitudinal axis. One was about its circumferential axis, it was 542. And another is along its longitudinal axis. It is a weak axis. So it is seeing, you can see over here. How much is the difference? It is almost 20 times lesser than that of 542. The weld group centroidal distance in circumferential direction YLB, which is 14. So from where these values have come from, that has not been given in the software, and that's what make it more complicated for the people who doesn't understand how these values have come from. And whatever inputs you have put in, accordingly it will consider these values. Whatever value we have put in, are they correct or not? Let's understand. This is nothing but the weld group moment of inertia, or this is nothing, a red color represent the weld group. So it will be having a width of how much? 6. T16. T is nothing but the thickness of the lifting lug. So that is the inner portion. There will be no material, right? When we'll be doing the welding, so the welding will be only represented by this uh, annular space between this rectangular portion. So let's say WL, that is the length of that weld, what we have put in was 150. WB we have put in 28, 16 plus 6 plus 6, that is 16 plus 12, it was 28. And this entire length will be equal to 150 plus 6 plus 6. So it is nothing but 162. So if I have placed a value of WL is equal to 150, T is equal to 16, WB is equal to 28, then I will have these two rectangles which will be marked by this dimension 150, 16, 162 and 28. Now let's calculate its moment of inertia about its strong axis and about its weak axis. So when we are saying strong axis, means the higher dimension will resist the moment of inertia. So along the circumferential axis, it will be having a higher moment of inertia. How to calculate that? Moment of inertia is equal to BD cube by 12. For rectangle, it is BD cube by 12, but we don't want to calculate for this entire rectangle. It will be only this annular space. So it will be outer rectangle minus inner rectangle. So for outer rectangle, what will be its moment of inertia? In strong axis, BD cube by 12. And these values are in centimeter. We have put in the values in millimeter. So let's take the values in centimeter. So here 15 a cube into 1.6 divided by 12, correct? Here for outer cylinder or outer rectangle, what will be its total width? 162. So it is 16.2. So its cube will be there, 16.2 cube multiplied by the width, which is 2.8. That is for outer rectangle. For inner rectangle, its higher dimension is 150 mm. So it is 15 cube multiplied by 1.6 divided by 12. Hmm. So we can say for outer rectangle, it will be 16.2 cube into 2.8. And for inner rectangle, it is 15 cube into 1.6. So 15 cube into 1.6 divided by 12, it will give you 542.023. So if we compare, this is exactly the same value what we have seen over here. So whatever our assumption was, that assumption is correct. So 150 and 16. 160. So if we would have given this WL is equal to 2 times, then what would have happened? It have considered it 2 times. So 300 will be the size of that rectangle that must have considered, and 300 plus 60, that would have been the rectangular size what the software must have assumed, and accordingly it will increase the moment of inertia. But I are we going to give that 300? No, practically we will be giving only 150. So this is correct, and these are our assumptions which are 100% correct. Now let's understand what will be the moment of inertia in weak axis. So here the cube will be 2.8 and 1.6. So it will be 2.8 cube multiplied by 16.2 minus 1.6 cube multiplied by 15 divided by 12. So it will be 24.515. So you can see over here, it is evident from here whatever we have calculated, it is 100% correct. So this is the weak axis moment of inertia. This is strong axis moment of inertia, and that's the reason why I have said you earlier that WL should be equal to 150. Now let's understand weld group centroidal distance in longitudinal direction. So you can see weld group centroidal distance in longitudinal direction. So it is 162 by 2. It is 162 by 2. So how much it is? 81. It is 81. So that's the value over here they have used. Then the distance of the weld group centroid from the lug bottom. From lug bottom where the centroid is, it is 150 by 2, isn't it? WL is how much? 150. So this value is nothing but WL by 2, and that's the reason why it is 75, which has been shown over here. Then weld group centroidal distance along the circumferential direction. So along circumferential direction, its moment of its width is 28. 28 by 2 is how much? 14. So that's the value which has been considered over here. So that's the reason why WB has to be width plus 2 times fillet size, and the length has to be only WL over there at the input. So that software will correctly consider all the dimensions, and we have seen that over here the dimensions are matching, right? The answers are matching with the software. Now once we have calculated that moment of inertia, let's calculate the forces. Axial force, we have given the value of 1732. Impact factor was 1.5, so the load has been increased to 2598. Similarly, for normal force, 1000 kg was the force what we have provided, and impact factor was how much? 1.5. So 1500 will be the load which will be utilized in calculation of the stresses. So first we are going to calculate the primary shear stresses in weld due to shear load. So now in that weld area, there are some stresses. In case of fillet weld, there will be always a shear stress. So in that weld, the shear stress will be generated, and that will be generated because of which kind of forces. So any force will create a shear in that weld area, because this is a fillet weld. So in any direction, it will be get sheared off. When it's sheared off, it will be sheared across its throat. So it will be sheared across its throat. So which force can create the shear force, or which can create the shear stress? Any force. So there are three forces: axial force, normal force, and tangential force. So tell me, axial force, normal force, and tangential force. and that's the reason why here the resultant force have been considered. So the resultant force will be calculated as square root of fx square plus fax square plus fn square plus ft square. So whatever force is applicable, its resultant will be calculated, and that resultant will be the actual acting force for that shear stress. So here fx square, ft square, fn square under square root. So here there is no ft, so that's the reason why this value will be 0. And these forces will be coming on the area. What is the area? That is a cross section area of that weld. So that is nothing but 2 times of WL plus 2 times of WB by 2. So Fx square, this is the resultant force, and total resisting area on the weld will be 2 into WL plus WB divided by 2 into WL into WB into weld size. So that will be the area over here, and then we will get the shear stresses. We will get the shear stresses over here. So that we are going to compare with the allowable stresses. So here you can see the shear stress value is hardly 152 kg. So it is hardly 15 MPa. It is hardly 15 MPa. Now we are going to calculate shear stress in the welds due to bending load. Shear stress first was because of the shear load, and now it is because of the bending load. Now what are the forces which are going to create the bending moment in that lifting lug? We have seen that one force was in vertical direction or perpendicular to, we can say, along the axis of that lifting lug. That was the force Fn. So normal force will going to create a tension, isn't it? Axial force can create bending, tangential force can create bending, but this normal force can never create bending, correct? So why they have considered this normal force in this? We can understood that axial force can create the bending. Axial force into off center distance will be the bending moment divided by its strong moment of inertia. Then tangential force by weak moment of inertia. You can see over here weak moment of inertia across the thickness across. So Ft is the tangential force into off center distance will create the moment, and divide by Z, that is section modulus, that is nothing but I by Y. So that is nothing but Y will come on the numerator side. So that is nothing but Y by ILL. ILL nothing but the weak axis moment of inertia, which is 24.515, and ILC is nothing but strong axis, which is 542. So these two forces are understandable. So that because as we can see over here, so the axial force is like this, so that can create a bending, and the tangential force, if it is there, which is inside going into the plane, that also can bend that lifting lug across its thickness. So these two forces can create the bending. But how this vertical force can create bending? Can it? It creates a tension. But then why they have considered it over here? Why they have considered that normal force in the bending stress calculation? The reason being, let's understand first. Stress is what? M upon Z. Stress is what? M upon Z. What is the M? Bending moment. Now let's understand, because of normal force, how the bending moment will be generated. If your normal force is not exactly at the center, if it is exactly not at the center, so there will be some eccentric distance between the center and the center of that vessel, center of that lifting lug, and that eccentric distance can create the that eccentric distance can create the bending moment. So you can see over here that eccentric distance, this can create the bending moment. If it is exactly at the center, then there will be no bending moment which will be coming because of this. But this is not exactly at the center, because of that there will be chances of bending moment which can create because of normal force also, correct? And this is the distance of our interest. And how to calculate that distance? That distance is nothing but h, that is this central distance, minus YLLB, that is the extreme fiber distance from the central axis. So H minus YLLB. But in our case, we have seen that 150 was the total length, and we have taken H exactly at the center, 75. So you can see over here, H minus YLLB, H was 75 and YLLB is also 75. So 75 minus 75 would become 0. So because of normal force, there won't be any force coming in our case, because we have taken normal force exactly at the center. But what if it is not exactly at the center? For that reason, they have included that H minus YLLB in picture, and because of that, the bending moment they have calculated and the stresses. Correct. So because of these all stresses, whatever are applicable, Ft is not in our case. So Ft you can see over here, Ft is 0. So this term will not be there. H minus YLLB is also 0. So this term will also not be there. So because of only axial force, there will be bending moment. So axial force will be how much? 1299 multiplied by off center distance was 100 into YLLB upon ILC, that is moment of inertia. So 81 into 542.023. Only this term is creating a bending stresses. So shear stress caused by the bending forces is 192.13 kg. Now we are going to calculate the pinhole bearing stress. Pinhole bearing stress means what? What is the area of the pin and the area of that hole which will be getting in contact with one another at the time of lifting. So it will be equal to the diameter of that pin which will be getting in contact with that entire hole area. So that will be equal to how much? That area will be equal to diameter of the pin multiplied by the thickness. And because of which force the pin can be under bearing, or the bearing force can be coming, or the two surfaces can be pushed against one another. You can see that there was one tangential force. That tangential force can move the pin along its axis, right? So it won't create any bearing, it can just slide the pin. But the other two forces, axial and nominal, normal force, can create the bearing. So here the resultant has been taken with reference to the normal force and axial force. You can see from here, axial force and normal force can create the resultant bearing force. So that has been considered, and what will be the bearing area? That will be equal to the diameter into the thickness of that lug. So the diameter of the hole, or diameter of the pin rather, dh multiplied by thickness. So this will give us the bearing stress. So that bearing stress also needs to be lesser than the allowable. Then the tensile stress at the bottom of the lifting lug. So tensile force is how much? Fn, that is a normal force. Only that force can create the tension. Neither the bending force or the tangential force can create the can create the tension. So here we can say the tension will be created only by the normal force. The tension will be created only by the normal force. So here we can see only because of this force there will be a tension coming. Because of this bending will be coming. And because of the inner force or the tangential force, there will be bending can be coming. But there won't be any tension because of these two forces. So tension can be created only by the normal force. And that's the reason why in that formula we can see the normal force was considered. So here normal force divided by the base area of that lifting lug. That is nothing but the width of that lifting lug and thickness of that lifting lug. That's the reason why the area is W into T. So this is how we are going to calculate the tensile stress. So we have calculated bearing stress, shear stress in weld, shear stress in the shear stress caused by the bending forces, shear stress caused by the shear forces, then bending stress in the lug, then tensile stress in the lug, shear stress in the lug, and total combined stress of the base at the base of the lug. The total combined stress means the bending stress and tensile stress divided by its allowable stress. And what is that value? So FBS is nothing but the total bending stress. FA is nothing but the total tensile stress. So addition of that, that should also be less than the allowable stress. So we are going to compare these stresses with the allowable stresses, and those stresses have to be lesser than the allowable stress. Once it is there, then we can say our design is safe. So we have checked the design for tension, shear, bearing, and combined stresses. And after that only we can say that our stresses are lesser than the allowable stresses, and hence the design is safe. Let's have a look at one video which is going to tell us how this lifting arrangement and how this procedure will be actually happening inside. So you will be having some feel of the lifting analysis, how important it is. If any lifting lug fails, then that equipment will fall down and the people may get very severe effect because of that. Other people may can lose their lives, or they can be disabled. So it is very very important. This is not given in the code. Code does not tell you anything about non-pressure part. Code is more concerned about the pressure part. but lifting lugs and these non-pressure parts can be equally or rather more important, because the code has not given any guidelines for that. So that is how it is more important to consider all these factors. So let's have a look at this video. So you will get overall idea how that horizontal equipment will make vertical, how these two trunnions, one lifting lug, one tailing lug will come into the picture, how that procedure will look like. So let's have So we have seen in this video also, there were tailing lugs and there was trunnions. So the trunnions were used for the rotation purpose, and lugs were used for the uh, only at the initial lifting purpose. And thereafter, the trunnions will get the rope along the trunnion will get rotated, and then the equipment becomes vertical. And when it becomes 100% vertical, the tailing lug and its rope was removed. Rather, the rope on the tailing lug has been removed, and the entire load was coming on the only the lifting trunnion. That was what we have seen. When it was horizontal, the both loads will be distributed on the lifting and the tailing lug, and once it becomes 100% vertical, the entire load has been transferred to what, the trunnions only. So that is very very important to understand, and this is how the actual twisting will be done, actual rotation will be done. And this is how one crane will be at the bottom, one crane will be used at the top, and this is how the twisting will be done, and then it will be placed at the desired side. So this is very very important. It take a days also, many a times. If it is a very huge equipment, then it can take days also for the erection process, or for lifting and erection purpose. So that is very very important. Very high capacity cranes will be used. So please do remember that this is a very very important parameter of your designing of lifting lug or the trunnion.